recursion definitions. We have looked at them before when we've looked at recursively defined sequences, so it's not something totally unfamiliar. But we're also going to look at structural induction in relation to this. And the idea of recursion is a process that you're going to keep doing time and time and time again, but maybe on a smaller scale. But it's the process of defining an element in terms of itself. So we'll do a process and then do it again, but do that same process again with a different parameters. But here's a classical example. At the right, you see where a large triangle has been subdivided by putting a dot on, in the middle of one side, and a dot in the middle of the other side, and a dot in the middle of the bottom side, and then connect those dots and you have another triangle. And then you do that same thing again. Each of the triangles, such as this top triangle, you subdivide and draw a dot on each of those sides, and a dot in the middle here, a point in the middle, and then you connect those points and you have another triangle. And you do the same thing for the bottom triangle and the triangle on the right. And then you do it again. Like, for example, this triangle right here, this point in the middle of this left side and the point on the middle of the right side and a point in the middle of the bottom were connected to form another triangle. And you just keep doing this time and time and time again. And you have what is called a fractal. A fractal is a figure that is formed by a recursion process. And you could have fractals of all kinds of types, and it's just this recursion formula where we keep doing the same process over and over again to different parts of the figure, and this can go on forever, hypothetically. Now, recursively defined functions involve specifying initial values and then specifying a rule for finding a later value from those initial values using what is called a well-defined function. So a well-defined function is just one where there's no doubt about how you can get the next value from the current value. So here's an example. Suppose G is defined recursively as G of 0 is 2, so that's your initial value. G of n plus 1, that's your next term you're looking for, equals 5 times G of n, that's the current term, minus 7. So it asks for us to list the first 5 terms of G of n. All right. Well, the first term, G of 0, that's already given to us. That's 2. G of 1, we take and go 5 times G of 0. Well, that's because if I'm looking for G of 1, n is 0 because this is looking for the 0 plus 1 term, which is G of 1. But it uses G of 0. And so G of 0 we know is 2. So we're going to go 5 times 2 minus 7, which we did here. And that comes out to 3. Then G of 2, well, you take 5 times G of 1 minus 7. So that would be 5 times the previous thing we found, which is 3, minus 7. So 15 minus 7 gives us 8. And you just keep doing this. 5 times G of 2. Or G of 3 would be 5 times G of 2 minus 7, so 5 times 8 minus 7, and you get 33. And then G of 4 comes out to 158. So those are the terms in the sequence. So it's very similar to what we've already done with recursively defined sequences. All right, let's look at how to convert a formula or a sequence into a recursive definition of the sequence. So here's an example. It says give a recursive definition for the summation from k equals 0 to n of a sub k. Now a sub k is just the term with subscript k, and all we're doing is adding those terms up. All right, so this is really the same as going a0 plus a1 plus a2 plus a3 all the way to a sub n. So can we, instead of using a sigma notation, can we make a recursive formula for this? Now first, we can define the initial value, a0, as the summation from 0 to 0 of a sub k. Of course, you're only going to have one term then. It's just going to be a0. Then a rule for finding the next term of this series, when it's added up, it's really a sum. All of these terms are sums, not just a single term. Anyway, it is, you can say, the sum from 0 to n plus 1 is equal to the sum from 0 to n of a sub k. So that'll add up all the terms from 0 up to k, and then plus a sub n plus 1. In other words, just add the next term to the sum from 0 to k, and then you'll from 0 to n, and you add the next term, and you'll have it going from 0 up to n plus 1. So this is a recursive definition, this along with the initial value definition, and you have a recursive definition. Now, Fibonacci numbers are a special sequence that come about in a lot of different areas of math and in nature. Shells and sunflower seeds and all kinds of things in nature have Fibonacci sequences in them. I don't know if you knew that, but Fibonacci numbers are F0, F1, F2, etc., and they are defined by the following recursive definition. F of n is equal to F of n minus 1 plus F of n minus 2. That means we're going to add up the previous term and the 1, 2 before the term we're talking about. So the n minus 1 term, which is just 1 before the term, and then the n minus 2 term, which is 2 before the term. So basically just takes the previous two terms and adds them up to get the next term. But you have to have two initial values. You have to say f0 is 0 and f1 is 1. That starts you out in the sequence. So if we added those two up, 0 plus 1, we would get 1. So f of 2 comes out to 1. But then you don't add the 0, you add the 1 and the 1 from the term we just got, and the 1 from the f of 1 right here. And the next term in the sequence would be 2. All right, then you add the previous two terms. So you'd add 1 plus 2, and you'd get 3. Then you add the previous two terms, and you'd get 2 plus 3, and that would equal 5. All right, then the previous two terms would be 3 and 5, and that would add up to 8. And then 5 and 8, that would add up to 13. So the terms in the sequence would be 0, 1, another 1, and then 2, and then 3, and then 5, and then 8, and then, let's see, 5 and 8 makes 13, and then 8 and 13 makes 21. So it just starts going up a lot more quickly afterwards, but that's the Fibonacci sequence. You can study this on your own, of course. Now, example 4 on page 347 provides a proof that for n greater than or equal to 3, any Fibonacci number with subscript n, so the nth Fibonacci number, will be greater than alpha. Now, that's not the letter A, that's the Greek letter alpha, but alpha to the n minus 2 power where alpha is this number 1 plus the square root of 5 divided by 2. All right, that's a pretty interesting discussion or derivation of why we use this number 1 plus the square root of 5 over 2, and why any Fibonacci number is greater than alpha to the power of n minus 2, where alpha is this number. But it comes from the fact, and I make a little note here, alpha is the solution to the quadratic equation x squared minus x minus 1 equals 0. And there's a reason why you come up with that equation when you do the proof. But you could take a look at it on page 347. Now, let's look at some examples similar to what you might encounter in the textbook homework problems. Here's an example. Find f of 2, f of 3, f of 4, and f of 5 if f is defined recursively by the initial values f0 equals -1 and f1 equals 2. And we're going to define this recursive, or we're going to find these numbers for n equal 1, 2, 3, all the way to infinity, but we only have to go up to number 5. All right, so the first example, f of n plus 1 equals f of n plus 3 times f of n minus 1. So let's say that n is the current term. Well, this is saying that the formula for the next term, n plus 1 term, f of n plus 1, equals the current term, f of n, plus 3 times the previous term. Okay, that's how you should read this. The next term equals the current term plus 3 times the previous term. Okay. Now, we are told that in the instructions that f of 0 is -1 and f of 1 is 2. So we have what the 0 term is and what the first term is. And so all we do to find a term is take the current term plus the 3 times the previous term. Now, if we're on this term here at, when n is 1, that's the current term. So to get the next term, we take the current term plus 3 times the previous term. So it'd be 2 plus 3 times -1. Now 3 times -1 is -3, and 2 plus -3 is -1. So that's the answer for f of 2. You get -1. Now, in the next case, we again take the current term plus 3 times the previous term. So the current term is -1 plus 3 times the previous term. Now the previous term is 2, so -1 plus 6, and that comes out to 5. All right. So you see if you can figure out what the fourth term would be. Well, the current term, you're going to make the third term, which is 5. So we go, what? Yeah, the current term plus 3 times the previous term. So if the current term is 5, we go 5 plus 3 times -1. Now, 5 plus 3 times -1, that would be +2. So for 4, we get +2. And then to get the fifth term, my mouse keeps disappearing. It's frustrating. The fifth term, we go the previous term, which we said was 2, plus 3 times the previous, or the previous term. So the current term, which is 2, plus 3 times that. So we get 17, because 2 plus 3 times 5 is 17. All right, so I hope you got 2 and 17 for these terms. Then, in the next example, it's a little bit more complicated, but it still uses the current term, f of n, and the previous term, f of n minus 1. But it squares them and multiplies them by 3 and -4. All right. So the next term is 3 times the current term squared minus 4 times the previous term squared. So if your first two terms are -1 and 2, it says go 3 times the current term, which would be the 2 here, 3 times 2 squared, minus 4 times the previous term, which is -1 squared. So this 2 squared is 4, 3 times 4 is 12. Here you're going to have 4 times 1, so that's going to be 4. So 12 minus 4 is 8. All right, and then in the next example, we take the current term, which is 8, but we go 8 squared and multiply by 3. 8 squared is 64. 64 times 3 is 192. And then minus 4 times the previous term, which is 2 squared. So 2 squared is 4 times 4 is 16. And you go to 192 minus 16, and you get 176. Now it's going to get pretty big. Actually, it's going to be very small, this next term, because you're going to go 3 times the, no, I'm sorry, very big, because you're going to go 3 times the current term, which is 176 squared. So we got to go 3 times 176 squared minus 4 times 8 squared. So it's going to be a pretty big number. I'm not going to figure that out in the video, but you can. But you know, then the fifth one would be very, very large. All right. So let's look now at number 2. Says determine whether each of these proposed definitions is a valid recursive definition of a function f from the set of non-negative integers to the set of integers. Okay, so we just want to see if this is a valid function or well-defined function. If f is well-defined, find a formula for f of n when n is a non-negative integer and prove that your formula is valid. Now, I didn't do the proving that your formula is valid thing, but you could just plug it into this and see if it works. So you're given the initial condition f of 0 is 1, and then you do, or then you have this that says a term equals negative of the previous term. So that's all it is. The opposite of the previous term. F of n minus 1 is the previous term. So this is well defined because we have a starting term, f of 0, and when we are trying to find f of 1, then n would be 1, and so 1 minus 1, that would be f of 0, but we have what f of 0 is, which is 1, and we can get the next term using this formula. So it's well defined since we know those things. And then the formula, well, I just thought about, what would you get? It'd be the negative of the previous term, so it'd be -1, and then you plug it in again, and it does the negative of -1. So now we're back to +1. And then we put in it again, it's going to be the negative of +1. So this is just alternating, +1, -1, +1, -1. So a way to express that in a formula is f of n equals -1 to the nth power. Because when n is even, or 0, that would come out to +1. When n is negative, it would come out to -1. And so it would be alternating as n goes from, even, odd, even, odd. So it alternates between +1 and -1. Now in B, we have f of 1 is 1, so they tell you what the first term is. They have f of n is f of n minus 1 plus 3. So that means take the previous term and add 3 to it. So the next term would be, oh, and by the way, we only are defining this for n greater than or equal to 2. So the second term would be, well, f of 2 minus 1, which is f of 1. f of 1 we know is equal to 1, so we'll have 1 plus 3. Well, that will be 4, okay? Well, then plug in 3 for n, so we got f of 3 minus 1, or f of 2, but f of 2 is the answer we just got, which is 4, so then we'll go 4 plus 3, and it'll be 7. And so each time it's adding 3 to the previous value, starting at 1. So we start at 1, and then we have 4, and then we have 7, and then we have 10. So a way to define this, or a formula, would be negative 2 plus 3n. Now, where did I get the negative 2? Well, I know that f of 1 has to be 1. And so if I plug a 1 into this, we have 3 times 1 is 3. Add that to the negative 2, and you have 1, which is the first term that we wanted. So I had it originally as 1 plus 3n, but that didn't work because when n was 1, it didn't give us 1 like it's supposed to. So I made it a negative 2. All right. Okay, so now we have some more examples to help you. It says, give a recursive definition of the sequence a sub n, where n is 1, 2, 3, etc. If, and then, so now you have a problem where you're given a formula and you have to come up with a recursive formula. So a sub n equals 4n minus 2. Now, if you plug in 1 and then 2 and then 3, you'll find that the first term is 2, and then the next term is 6, and then the next term is 10, and it keeps adding 4 every time. So the initial term is 2, and 4 is added each time. Thus, we can define this as a sub n equals the previous term, a sub n minus 1, plus 4. See, that's what you got to get used to, this notation. A sub n is the previous term, a sub n minus 1, plus 4. Now, this is not using functions. It's using a sub n, or a sub n minus 1, and all that. Anyway, but your initial term needs to be defined. And your initial term is 2, because when you plug in 1, this will give you 2. But that's your recursive definition there in the red color. Now, a sub n equals 1 plus negative 1 times n. Well, we're starting, I'm sorry, if we start with 1 and plug in 1, we're going to have 1 plus negative 1 times 1. So 1 plus negative 1, and that would add up to 0. So our first term is 0. Then we plug in 2. Well, 1 plus negative 2, that's negative 1. Then we plug in 3, so that's 1 plus negative 3, etc. And so you get these numbers 0, negative 1, negative 2, dot, dot, dot. So it looks like it's starting at 0, and then it's just going down, negative 1, negative 2, negative 3, negative 4, etc. So you're subtracting 1 every time. So what I'm saying is I could write my recursive definition as a sub n, the next term, equals the previous term minus 1, because we're always just going to subtract 1 from the previous term. And then your starting term is 0, so a sub 1 equals 0. All right, if you plug 1 in here to this next example, you get 1 times 1 plus 1, which is 2, so 1 times 2 is 2. You plug in 2 there, you get 2 times 2 plus 1, which is 3, so 2 times 3 is 6. You plug in 3 there, you got 3 times 3 plus 1, which is 4, so that's 12. 4 times 5 is 20. 5 times 6 is 30. So here are your terms, 2, 6, 12, 20, 30. Now, this is different because we're not adding the same thing every time, and we're not multiplying by the same thing every time. So it's not arithmetic and it's not geometric, but you'll notice that between 2 and 6, you're adding 4. Between 6 and 12, you're adding 6. Between 12 and 20, you're adding 8. And next one, you're adding 10. So you're adding an even number every time, the next higher even number every time. And by playing around with this a little bit, I found that all I have to do is just add a plus 2n, because you take the previous term and you add 2 times n. Now, why did that work? Well, when you're looking for the second term, you add 2 plus 2 times 2, because 2 times 2 is 4, so 2 plus 4 gives you the 6. When you're looking for the third term, you add 2 times 3. So you're always adding 2 times the n, or the subscript n, to get the next term. All right, so this formula will work if you start with your first term being 2. All right, and then positive multiples of 7. Well, the terms are 7, 14, 21, etc. That's the positive multiples of 7. So our starting number is 7, and we're adding 7 every time. So we can write it recursively as a sub n equals the previous term plus 7. And then we just have to start it off as 7. Okay? Now, concatenation is basically a simple concept. It's just taking 2 strings and combining it into one string. So strings are combined by concatenation when the characters of the first string are placed first, then the characters of the second string are placed in the string. It's like if you had one string for the first name and one string for the second name, the last name of a person, and you wanted to combine it into one string for their full name. That's what you would do. All right. So if 2 strings W1 and W2 are joined by concatenation, we write W1 dot W2 or just W1 W2. I like the second notation. The dot makes you think you're multiplying, and you're not really multiplying. And the length of the concatenation will be the length of the first string plus the length of the second string. Now, this is used in a homework question, so I wanted to mention it. But you could define a recursive definition where you're recursively adding a string on, and it would just get a longer and longer string. Now, I want to talk about recursive algorithms, section 5.4. Now, you know that an algorithm is something is recursive when it keeps repeating that same process. Well, that's kind of what we're doing with a recursive algorithm, but we're repeating the process with a smaller input every time. So an algorithm is recursive if it solves a problem by reducing it to occurrences, repeated occurrences of the same problem with smaller input. So examples 1 and 2 on page 361 show such algorithms for computing n factorial and a to the nth power. So we're going to look at some examples of doing this using these algorithms. So I want to talk about the algorithms, but first, the command return is explained on page 940 if you want to look at that, but I'll give you a brief synopsis of what it means. But let's look at algorithm 1 when we do that. Algorithm 1 is a recursive algorithm, so I'm just telling you that, and it's for computing n factorial. And n factorial, if you recall, is the number times the next number down times the next number down, all the way down to 1. So like 4 factorial would be 4 times 3 times 2 times 1. Now, the procedure has a name factorial. That is the name of the procedure. And when we want to call it into action, we just give its name. Okay. Now, inputted to this procedure is a non-negative integer n. All right. So if you call it into action, you're going to call it with giving it what that n value is. But we can change what that n value is. Now, if n equals 0, then return a 1. Now, the purpose of this command is to stop it. You got to have some way to stop the recursion, okay? So that will stop it. Now, if it's not equal to 0, if n is not equal to 0, then it won't do this return 1. It will instead return n. I'm sorry, it will return n times factorial n minus 1. Now, what in the world is this doing? Factorial is not a variable. It's actually the procedure itself. So it's calling into action the procedure itself. It's like calling itself into action, but this time with a value of n minus 1. Or in other words, a value for n that's 1 less than it was before. Okay? Now, it's going to take and multiply n times the procedure result, or what this procedure factorial n minus 1 will return. And so it'll just keep multiplying n, and then it does the procedure using n minus 1, so it'll multiply by n minus 1, and then it does the procedure using n minus 2, and it just keeps multiplying by n minus 2, n minus 3, all the way down until it reaches, when n is 0, it'll return a 1. Okay, and we'll look at that when we trace this. The algorithm 2 is recursive, and it's for computing a to the nth power. It says procedure power, and it brings in two things: the base, which is a, and n, which is the exponent. So it will repeat this process until the exponent's down to 0, and then it'll return a 1 there. Anyway, then what this does is returns a times, and then it calls into action the procedure itself with a lower value for n. Instead of n, it'll do it with a lower value, n minus 1. So this is a very powerful type of algorithm, recursive algorithms. In just one line, this procedure has like one line, it can do a recursion operation, or set of steps, and rather than having to write a several loop, or several line loop program. All right, so it calls it into action with a lower value, and then it just keeps repeating that call to action until n, the number here on the end is down to 0, and then it returns a 1. And we'll see what this does. All right, so let's look at algorithm 1 and what this does. So it's the algorithm we just talked about on the left side of the previous slide. And it says here is a trace of algorithm 1 when n is 4. So it begins the procedure with this command procedure factorial, and it inputs the number 4. So it begins the procedure factorial 4, and then it ignores this because n is not 0, and it hits the else part, and it returns 4 times factorial n minus, or 4 minus 1, because n is 4, so it's gonna plug into that factorial procedure, this procedure, 4 minus 1. So this is a call to action to do the procedure again. So it begins the procedure using factorial 3, in other words, when n is 3. And then it does the else by returning 4 times 3. Now notice it's going to still remember that it was multiplying by 4, and then it multiplies by n again, which is now 3, and then does factorial 3 minus 1. So then it calls into action factorial 2 now, because 3 minus 1 is 2. and then it remembers that it had gone 4 times 3, and then it multiplies by n again, but this time n is 2, and then it calls into action factorial 2 minus 1, all right? And then that's the same as factorial 1, and then factorial 1, when it does that, well, n is 1, so it's going to remember the previous 4 times 3 times 2, and then it's going to do this 1 from the n here, and then it'll do factorial 1 minus 1, which is factorial 0. But when it begins procedure factorial 0, then it encounters this line, if n equals 0, then return 1. All right, so it does that because n is now 0, and it returns 1. Now, it doesn't return a new call to another procedure, so this is where it stops the iteration or the recursion. And so it'll just multiply by a 1. Now, we already had a 1, but this is going to be a 1 also because it's going to return a 1. And so we'll have 4 times 3 times 2 times 1 times another 1 from this. And so that's the same as 4 factorial, though. Now, you don't need the 2 ones. Just 1 would be sufficient, but it doesn't hurt anything to have that other 1. So it's going to basically return the number 24, which is the same as the factorial. So I hope you see the recursive nature of this, how it's calling it into action the same procedure, but with a smaller inputted value. All right, so in the same way, this second algorithm computes a to the nth power. Oh, that should say a to the nth power. For some reason, that didn't carry in as an exponent. All right, so this procedure does the same kind of thing. If n is 0, then it'll return 1. Else it'll return a times power. But then it has 2 inputs this time. Now, a is always going to be inputted because that's always going to be a. But n is going to be lowered every time. It's going to input, 1 lower. So if a was 2 and n was 3, that means it's going to be computing 2 to the third power, which I know you know is 8, but the computer needs to see that. All right, algorithm 2 is also a recursive algorithm that is to compute a to the nth power. It does the recursion because what is a to the nth power? Well, it's a times a times a times a n times. So you can compute this using this procedure as follows. Procedure power, and so it calls into action and inputs 2 things. It inputs a, the base number, and n, the exponent. Okay, so this time we have 2 inputs. Now, if n is 0, then return 1. So that just means it gives us a way to stop the procedure. And it'll return 1 when it gets done. And then else return a times. And then here is another call to a procedure, but using a smaller n value. Now, it still uses the same a, the same base for the exponent, but it calls it into action again with a smaller n value. Okay, so it's going to produce a times the lower power value. So here's the trace. So suppose a is 2 and n is 3. So in other words, we're computing 2 to the third power, which you know is 8, but let's follow the procedure. So it begins the procedure using 2 and 3, because that's how it would input these if you told it to use those values. Does the else, then it does the else command because n is not 0, so it'll do the else command, and it returns a times, so it returns 2 times power 2 comma 3 minus 1 because it's subtracting 1 from n. So it's going to basically have n is 2. So it's going to do the procedure using a is 2 and n is 2. Okay. So it begins the procedure with smaller input values. Now it again hits else because n is not 0 yet, and it returns a times the procedure. But this time, so it remembers the first two, and now it's doing another two from the command, and then it drops the value of n down. So now we have a sub 2, or a is 2 and n is 1. But then it begins that procedure again, and it returns 2 times another 2. But then it calls into action the procedure using a is 2 and n would be 0. Now, when it gets to the procedure with n is 0, it identifies that n is 0, so it's just going to return 1. It's not going to call the procedure into action again because it just has the number 1 there, not a new call to the procedure. So then it will produce a 1 on the end. So it will go 2 times 2 times 2 and then times 1. Okay. And that would, of course, result in 2 to the third power, or 8. So another example is a recursive algorithm to find the greatest common divisor of two integers, a and b. Now you need to have a less than b, okay, in this. And so we're going to do, it uses the fact that the greatest common factor of a and b is the same as the greatest common factor of b mod a. Okay, b mod a is the remainder. And so we did the Euclidean algorithm, and we were constantly using that fact. So here's the procedure. It brings in a and b, two integers with a less than b, and then this is the way to stop it if the remainder is 0. Remember the Euclidean algorithm? We stopped when the remainder is 0. And it'll return b, which will be your greatest common divisor. And then it's going to return, if a is not 0, then it's going to return the greatest common divisor of, and that's a call to start the procedure over again, but using a smaller value for the a. It's going to use the remainder, b mod a, for the a. And notice now the b has switched out, and the b's gone, and now we're going to put a in the place of the b. Okay, because now a will be the larger number. The remainder will be smaller. The b mod a, that's the remainder, that will be smaller, and a will be the larger one. So it just does the Euclidean algorithm, basically. So let's follow this in this situation. And I would like you to be able to trace an algorithm through. If I tell you some starting numbers to start with, you should be able to tell what it's doing and trace it through. So it begins the procedure using a is 6 and b is 15, and then does it'll hit the line that's if a is equal to 0. So it's not going to do that line, but it does the else instead. So it does the else and returns the GCD of 15 mod 6 because it's doing b mod a, and b was the larger of the two. So it does 15 mod 6. Now, what's the remainder when you divide 15 by 6? Well, 6 goes into 15 twice with a remainder of 3. So that is going to do 3, or use 3 now. So now it begins the procedure because we're calling into action the procedure, but using 3 and 6 instead of 6 and 15. So now since a is not 0 yet, it returns GCD of b mod a. So in other words, it does this switching again. So it does 6 mod 3, which is, the remainder when 6 is divided by 3, which comes out to 0. And then it puts in the new B value, which our new A value, which is now 3. And so it calls into action. That calls into action the procedure, but this time with the GCD of 0, comma 3, or the GCD of those two. Now in that case, your A value is 0. So it hits this if A is 0. So it's going to stop the recursion and return what B is. Now B is 3, so it's going to return B, and B is the greatest common divisor of 6 and 15, isn't it? Both, 3 goes into 6 and 3 goes into 15. It's what we call the greatest common divisor of those two things. So you should be able to, trace an algorithm like this. Now, here's give a recursive algorithm for finding the sum of the first n even integers. So this is a recursive type algorithm that you can create. Now, here's my thoughts about how you would create this. First, think about how you can produce even integers. You remember that even integers are always in the form of 2 times k, where k is an integer, right? All right, now, I took an example situation. I just chose, let's say that n was 3. I could have used n was 4 or n was 5 or whatever, but I just said, let's suppose n is 3. So the integers that we would be summing up, because it says the sum of the first n integers. So we're going to do 2 times 1, because that's the even integer 2. 2 times 2, which is 4. 2 times 6, which is 6. I'm sorry, 2 times 3, which is 6. So we're adding up all the even integers. So here's an example. But if we wanted to use a recursive thing, we would always be adding the last integer on to the previous sum of the integers. Okay, we want to be adding, that n plus 1th term to the sum of the previous n terms. That's one way you could think of it. Or I'm sorry, adding the nth term to the sum of the previous n minus 1 terms. So that's the way you could think of it. And the nth term would be 2 times n, right? Because if n is 3, then 2 times 3 would be the next even integer that we want to add. So all we have to think about is, how do I add the next term, in this case 2 times n, to the previous sum? And so the recursion algorithm, let's call it even sum, all right? Calls into action, it inputs n, whatever n is, if you want to ask it to produce the sum of the first 7 even integers, or the first 13 even integers, or whatever. So n would be how many you want, okay? And then we're going to stop it when n is 0. So we're going to return 0. Now, why do we use 0 instead of 1? Well, we don't want that last step to hurt anything. When we were multiplying, when you multiply by 1, it doesn't change anything. But if we were adding on that 1 would change it, okay? But now that we're adding, we got to add on 0, okay? So that's why returning 0 is what we want to do here, because we don't want that last step when n is 0 to do anything, really. Okay. Now, the else part of this is to return the sum of 2n, which was that new term, plus the previous sum. So this is the recursion call, the call to repeat the algorithm. So it's going to give the sum of the previous n minus 1 terms is what this is going to give, because it always adds 2n plus the previous sum, and it's just going to always add 2n, and so it's going to even sum n minus 1 is going to add up all the terms the previous n minus 1 even numbers, okay? Because it's calling itself into action. So this right here, this one line, this one if then else command will do what you have in this example. Recursive algorithms are pretty cool if you can understand how they work and how to create them. All right, one more example. Give a recursive algorithm for finding the minimum of a finite set of integers using the fact that the minimum of n integers is the smaller of the last integer in the list and the minimum of the first n minus 1 integers in the list. So see, let's say that every day you would add a new number to a list of numbers, but you didn't get that new number until that day. So you wanted to find the smallest number in that list. Okay, so you could figure out the smallest number on the first day. Well, that would be just that number. Figure it out on the second day. Well, that would just be the smallest of those two. And then when that third day comes along, now you take whatever the smallest is of all the ones before it and compare it to the third day's number. So that's kind of what this is doing. We're going to be comparing the new number to the previous, all the numbers before that. So that's what the min command does, by the way. So instead of a loop, as the directions say, we recursively call into action the procedure to find the smaller of the last integer and the minimum of the first n minus 1 integers, stopping when n equals 1. Okay? Then it finds the minimum of all the ones before it and the last number. So here's the procedure. Procedure smallest, a1 ... all the way to a sub n integers. If n is 1, then return a sub 1. So it always, needs somewhere to stop. And so this is what you do when you're using this minimum command. And then you go else return the minimum of, and then it calls into action the program itself. Notice it has the same name as the program itself or the procedure itself. And then it checks from A1 all the way to A sub n minus 1. Now if so it's just going to keep calling itself into action several times. And you'll see this when we trace it. Anyway, but you can read this key and think about that. Okay, so let's look at a trace of this procedure. And in this trace, these are the numbers that we're going to plug in. We're going to plug in 12, 5, 3, and 8. 12, 5, 3, and 8. So those are your list of integers that will be inputted into this program because it's inputting a list of integers. Okay, so it begins the procedure and it inputs 12, 5, 3, and 8. And n is 4 in this case. So it knows how many there are. N is 4. And so n is not equal to 1. So it will go on and do this else return minimum of. Okay, so it's doing this minimum of, but then it calls into action the program again. But this time with one less. So it's not going to look at the last term because it's looking at the terms before the last term. So it's calling into action the smallest 12, 5, 3 procedure. And so it begins the procedure smallest 12, 5, 3. Now this time n is 3, but it still continues. And now it does the else part and it comes in here and it calls into action the smallest, but this time without the 3 because it's always dropping 1 off the list when it does this, okay? So it treats the 3 as the a sub n term now. All right, but then that calls into action the program for 12 and 5. Now, it begins that procedure. Now, this time n is 2. It does the else by returning smallest of 12, comma 5. So it's dropping the 3 off of it and just looking at the 12 and the 5. Now, n is 1 this time, and the if-then statement here says if n is 1, it's going to just return a sub 1 back to the program. So it's actually going to be just returning the 12 as the a sub 1 back to the program, but it's going to send it back up to the 12-5 comparison. So it does the minimum of 12 and 5, which is 5, okay? And then that is sent back up to this right here, the minimum of 12 and 5. So it's going to compare now 5 and 3. So it does the minimum of 5 and 3, which is 3, and it sends that up to this comparison of 12, 5, and 3. So it then does the minimum of, or I'm sorry, this is where I should have pointed right here. The minimum of 12, 5, and 3 is 3, and then it compares 3 and 8, and it finds the minimum of that is 3 also. So it's done when it gets to that. So it's got to go back up. It's kind of like, you know, plugging it back in until it reaches back up to the beginning where it started. That's kind of what the return command does. Returns the consideration of what you're looking at. All right, so try to understand this. You might need to study it some more, but give me questions if you have any. I'd love to help you. All right, take care. Bye.